10, 9, 8. If you've had surgery, you probably remember breathing through a mask and slowly counting backward. Then, what feels like a fraction of a second later, you wake up. The multi-hour operation is already over. It feels like you took a very quick nap, but you weren't actually asleep. Sleep is a natural, restorative state. You were under anesthesia. This is a highly complex, artificially induced state, where you are totally unconscious, unable to form memories, physically paralyzed, and completely immune to pain. Without the ability to perfectly pause your consciousness and block those pain receptors all at once, the sheer physical trauma of a modern surgical procedure would be unsurvivable. Pain travels through the nervous system as a series of electrical impulses. It's a vast network acting like a biological highway, constantly sending distress signals from your body up to your brain. Regional anesthesia targets a specific location in the body to sever that highway before the electrical signal can travel any further upward. The localized numbing effect was actually discovered by accident when an ophthalmology intern managed to get a drop of cocaine on his tongue. Look at this cross-section of a neuron's cell membrane, featuring specialized protein gateways embedded in the surface. Regional anesthetics bind directly to these proteins. The drug physically locks these gates. Positively charged particles try to get inside, but they're completely shut out. By starving the neuron of that positive charge, the electrical pain impulse cannot move forward. It is chemically trapped at the surgical site and erased from reality before your brain ever registers it happened. For major, invasive surgeries, numbing a single area isn't enough. Doctors have to induce a total blackout of your entire central nervous system. This practice, known as general anesthesia, traces its roots to the 1840s. Doctors began repurposing recreational drugs like diethyl ether after noticing that people at parties would completely ignore severe injuries while under the influence. By the 1870s, the field evolved to include intravenous agents. Today, doctors combine specific sedatives like propofol to induce unconsciousness with opioids like fentanyl to blunt pain. This zoomed-in brain neuron highlights the GABA-A receptor gateway. General anesthetics target this, wedging the gateways permanently open. A massive flood of negatively charged particles rushes inside the cell. This sudden buildup acts as an electrical logjam, completely preventing the neuron from transmitting signals. Normally, an awake brain relies on a chaotic chorus of constant electrical cross-communication to keep you aware of your surroundings. Under general anesthesia, that massive cellular logjam forces those signals to become unnervingly calm and organized. The different sectors of your brain simply stop talking to each other. This forced neurological silence temporarily dismantles the very network that creates human awareness. This is a highly toxic process. Early anesthetics relied on literal poisons like hemlock, and even modern drugs severely depress vital functions like your heart rate and your breathing. This requires an anesthesiologist. Their role is that of a master chemist, actively orchestrating your survival. Their real-time challenge is to constantly adjust the precise cocktail of regional, inhaled, and intravenous drugs. They must keep you hovering in the microscopic window between waking up mid-surgery and suffering lethal organ failure. Mastering this chemical tightrope walk allowed surgeons to invent incredibly complex, life-saving procedures, from routine C-sections to replacing entire damaged livers and kidneys. So the next time you find yourself staring at those bright lights and counting backward from 10, remember, you are submitting to a perfectly engineered, completely reversible pause on human consciousness.